spreadsheet where I can simply add hotkeys by adding them here with the Edit Add button. And you can see I've created a hotkey that's called FEA modes, and that's going to execute a script called VSL. Now that stands for Vibrant Script Language or Scripting Language. So we've put some new terminology in here to support this scripting. This is all relatively new in Emyscope. So you'll have to get a current download from our website if you're on support, and you will be able to do the same thing and actually use this project. I can send you this project. If we have an email address, Mark, we can send that to anyone who's in attendance today. Hotkey icon. You can see I picked out an icon here for each of these. We've got a pick list of some of them that are available in Emyscope. We'll probably expand that in the future. These descriptions over here, I haven't really typed in one, so those are just defaults. So these are the main issues here in the use of hotkeys. Now you can see that I can also show them in our console software. That means they get passed through a database, a network database, to our console software, which we use for monitoring machinery and so forth. We're not doing that here, though. We're not trying to log data into the and control it or look at it in console. Anyway, let me close that, and I can push this hotkey as many times as I want, and it's just putting up animation here. Now over on the right is a set of mode shapes. It says first 10 SDM mode shapes. So where'd those come from? Well, let me just show you how we've set up this model. Underneath of the model that you're looking at is another model that we're using to drive the animation. And that has the modes of the first 10 modes of the base plate and the two bearing blocks. So this is something that's very easy to build in Emyscope with our FEA model updating option. So part of the option is the ability to add elements to a simple geometry like this. So as I click through these, you'll see the various modes. Now they're in RPM, which if I put that back to hertz, that's basically 0. These are rigid body modes. The rigid body modes, these were created with our SDM software by modeling the attachment of each of these bearing blocks with stiff springs to the base plate. So I simply solve for the rigid body modes or the FEA modes of the base plate, then the bearing blocks, and then I used SDM to attach them together. So these first 6 modes are all just rigid body motions of the bearing block and the two bearing blocks and the base plate. Okay, so here is the first bending mode of this structure. So it's a simple bending mode. You can see this is not completely symmetric, although this mode certainly is a nice clean bending mode. There's the first.
Dad, I don't want to interrupt you, but we do have a question.
All right, very good. Yeah, interrupt me whenever.
Let me go ahead. Yeah, we just got a question in from Mehdi Satara. And the question, you discussed the problem of curve fitting the structures that have changes in their resonance frequencies during a modal test. When curve fitting using the local fit, the damping depends on the band selected. Also, can you discuss the accuracy of estimation of modal parameters when curve fitting? Many times using different bands, Emyscope results in different modal parameters. It's like a two-part question there.
Okay. One is that using a local fitter in Emyscope, you get different frequency and damping values. So let's go ahead and I'm going to stop this because I was off here demonstrating some of the scripting. Let's go open up, let me see if I can find it here, my Jim Beam test article. I'm going to close that project and we'll open up the Jim Beam here. Okay, so here is Jim Beam. If I start animating the mode shapes, let's just start animating ODS data just to take a quick look at what we have here. So as I move the cursor band around, boy, that doesn't look very good, does it? Let's just put it on a peak here, and I'm going to stop this and create some new animation equations and see what. Sometimes I make changes to my projects so they don't animate the shapes very well. But the first thing you want to do is just go and animate shapes from. Okay, so we have a model here with extra points in it. I'm going to interpolate. Okay, so we're still getting some rather fuzzy looking animation here. Let's go curve fit this data. I don't like what I'm seeing in terms of one of the points. So, but let's just assume we got some good data here, and I'm going to go in and start the curve fitting. So the question was, if I use a local fitter, because my frequencies are moving around in my data set. Okay, let me just, oh, I see what the problem is here. We've got some window data that I saved away. Let me see if I can recover. Oh boy. I was doing some strange things here with this data. LMA curve fitting. What I'm going to do is see if I can. Oh no. Okay, let's go back here and I'm going to go out and see if I can find a good set of data. I was doing some windowing on this data, and that's what's caused it to be a little bit different than I would expect. But I will show you the case. Well, let's just go to this case right here. Here we go. All right, now I can answer that question. Let me just. All right, we're on linear magnitude. I'm going to go switch my y-axis to a log magnitude, which is what we normally look at. Okay, let me go back into curve fitting and show the case here that we're talking about. I'm going to overlay the imaginary peaks. We're in curve fitting. Let me turn off this and let's clear out all the fit data and let's overlay all the peaks. Overlaid. All right. Now what you can see is that out here at some of these higher frequencies, the peaks are moving around because the way we tested this model, let me put this down, is we impacted it out here at the end at 0.15. Let me just make this big and we'll take a quick look here. So we impacted out here at the end and we roved a triaxial accelerometer around on this structure. And that triaxial accelerometer was heavy enough so that as we moved it, the modes moved around in frequency because they would sense, depending on the mode, the presence of that mass differently as we took the data. Now in the low frequency modes, if you look down here at the low frequencies, let's just I'm going to zoom in here around a few of these lower frequencies, and then I'm going to amplify the peaks. If I put a line cursor in here, what I expect to see is all the peaks, all 99 measurements having a peak at the same frequency. And that's pretty much the case here at these low frequencies. Even up on this one here, if I expand it, I'll start to see the evidence of, I'm going to put the band cursor around here and expand the display in the Y direction. Now I want to go back to a line cursor and just put it. So what you can see here is that, see these peaks up here? When this mode is excited with a lot of motion, the peak actually moves down in frequency a little bit because of the effect of the mass loading. Let's go way out here to some of these higher frequencies now and take a look. Okay, so here's some right in here, and I'm going to set this back. Now here you can really see the effect of mass loading right in here. Let me zoom in here a little bit, and you can see that when the mode is really moving at those points, wherever they are on the structure, the effect of the mass is that those peaks move down in frequency because of the heavier mass. So the question is, what about curve fitting this kind of data? Here's another case right here where there is some mass loading. Let me zoom it up here or expand it. You can see that when the mode moves a lot, the peak is actually at a lower frequency. I can also put the band cursor on, or the peak cursor. Now you can see where it found the peak in each of those FRFs. There's 99 of them in here, and you can see when the peaks are very low, the frequency is higher, and as the peaks get higher, the frequency goes lower. Okay, so here we are in curve fitting. Now, if I wanted to curve fit this thing with what we call a global fitter, so now we need to come over here into the curve fitting tabs, and you can see I chose a global polynomial fitter. I can also choose a local polynomial fitter and then a multi-reference. Well, we don't have multi-reference data, so we're not going to use that one. But I've got a choice between global and local. And when the peaks move around like this, then I may want to use a local fitter because it will fit the data a little bit better, and my mode shapes might come out a little bit better. But the first issue is, what about the frequency and damping? So let's just try a global fitter here. And I'm all set up to use the quick fit. Quick fit will go through and it'll compute a mode indicator. There is none here. Then it'll curve fit in the band with the global fitter. Then it will go ahead and get the residues once it has the frequency and damping. So let me try that. I'm going to go ahead and do that. And bingo, you can see that it got a pretty good curve fit of all those measurements. There's a red line drawn on there. We may want to go back out of the overlay here just to examine the results a little better. And we can go to the magnitude. Oh, I thought I got out of the overlay format. Let's go back to row column. Okay, so here as I scroll through, you can see that the fit function, which is the red line, is not really lying on the, and let me turn this peak cursor off here. It's not laying on the data real good, because the global fitter found one value of frequency and damping. You can see what it is down in here. If I think hold down one of these keys here, I can get the value of that. Well, we've got the value over here, so we don't really need it from the picture. Now I'm going to turn the band cursor back on. Now I had to either peak cursor or band cursor, it doesn't matter because the fitter is only going to work in that band. Now I'm going to switch over to the into frequency and damping. So this is just for frequency and damping. Okay, polynomial method, where are you? Local polynomial, there it is. What that's going to do is curve fit each of the measurements and come up with a different value of frequency and damping, but when it gets all done, it's actually only going to put one value, well, no, it's going to put a value in the shape table for each measurement. See here, if I scroll through the measurements, the frequency and damping does not change. Now the residue is changing because I did a quick fit and I have a residue. So some of these modes, some of these measurements were, at least by looking at the overlay there of the fit function, it looks very good. All right, let's go through now and do a quick fit with the local polynomial method. So I'm going to go ahead and do that. Now I've got, let me scroll through here. You see how that frequency is moving around? You can see it in the picture down here, and you can also see it in the spreadsheet. Because of the mass loading on this mode, the frequency and damping are different with each one. And of course, the curve fit now is just darn near perfect. Even though I had mass loading in my data, this is just a practical issue. So now what do we do when we save the mode shape away? Well, there's where we average these values, all these local values of frequency and damping together. Now, are they a whole lot different than the global estimate? Well, yeah, some of them are. You can look at the values here as I have to drop the cursor, but you can see that they do change with each measurement. When I save the shape, now it's going to simply, let me just pick a new mode shape table here and put, oh, well, I only had the one selected, but I could put them both in there. Let's unselect and do that again. I'm going to replace. And what happened to my shape table? Well, let's do this. Okay, here it is down here. Here's the shape table. Now it's got different damping values because the first one, the first is a global, the second is a local. So let's go ahead and animate these and see what they look like. So we'll animate the shapes. Okay, that's a fairly high frequency mode. You can see there's a lot of complexity in it. Now let's animate the second one. A little bit cleaner because the local fitter used the local frequency and damping and got a cleaner estimate of the residue. Let me turn off the points here. Versus the global fitter, which you can see there's just a lot of complexity to the shape. Now I can take some of that out by telling it to just normalize. So there I normalized the shapes and I cleaned it up a whole bunch. So that, but if I don't do the normalization, then the global fitter, let me turn that off again and go back. You can see I got a nice clean shape from the local fitter, and there I got a more complex shape. So, Mark, that answered the question, I think, unless there's more questions.
Nothing at this time. Just wanted to make sure we got that second part, though. Discuss the accuracy of estimation of mobile parameters when curve fitting, many times using different bands, scope results, and different modal parameters. Want to make sure we just answer that second part.
Yeah, now there's two ways to answer that. One is we got a number up here called FRAC. That stands for Frequency Response Assurance Criterion. Now, where that came from, I didn't create this word. It's been created by some people at University of Cincinnati, specifically a professor there, Professor Randy Alamain, who did his PhD thesis on something called MAC, or Modal Assurance Criterion. Now, the Modal Assurance Criterion is a metric between two mode shapes. And the answer is 1 if the mode shapes are the same, and it's 0 if they're very different. And generally, the rule of thumb is that if the MAC value is less than 90%, then they are substantially different mode shapes. Okay, well, he took that same idea and he went ahead and applied it to fit functions, or the difference between two FRFs. So here we have the red line is the FRF fit function, and the data is the dark line. And you can see the frac value as I scroll through here is 1, because the local fit is putting the fit function right on top of the data in every case. Well, let's go back and select the global fit data, and now I'm going to go back to my residues and go ahead and compute those residues again for the global, just using the global fit data. So I'm going to do that right now. And you can see that now the fit function doesn't lay on the data anymore, because my frequency and damping is not matching up with the frequency and damping in this particular measurement. And now as I scroll along here, you can see the frac values are all 91%. Some of them are 99. There's one at 90%. There's a couple here at 89. You can see that the fit function's not laying on top. So what that's saying, just like comparing two mode shapes, now it's comparing to the fit function and the data itself. And so that is a measure or a metric of the difference between my raw data and my curve fit. And that is a measure of the goodness of fit, if you will. Now, statisticians would like a lot more statistics. They'd like to know the mean and the variance and the goodness, by different statistical measures. We don't have that in MeScope. We do have this frac value, and so that is telling me how well my fit function. Now there's a good one there. The frac is equal to 1. You can see that it's laying right on the data. I can also put up the Bodie. Well, so there's the phase and the magnitude, and you can see a very good fit there between the complex data, the magnitude and phase, and the fit function. Now let me find a bad one in here, and you can see that when it drops down below 90%, the curve fit is no longer as good as where it's not matching up with the data. There, let me go up here and find, okay, there's one at 89%. So that one is showing that the magnitude and phase don't match up. So that's the way that we can come up with a goodness of fit. Again, it's mostly, we don't save those numbers or anything like that. We have some other commands in MeScope where I can actually compare synthesized FRF. That's really what this fit function is, a synthesized FRF versus my experimental data, and save those into a shape table. So I can go ahead and document my curve fitting results a little bit better if I want to come up with some numerical numbers to compare the goodness of fit. But I think this example shows the difference between a global fit and a local fit. If I go back here and estimate the residues using, now my fit functions are all perfect. They lay right on the data. This is a resonance. I've got the negative going phase. I've got the peak at the resonance. But as you can see, as I scroll through here, watch the picture down below. The vertical line is showing me the frequency, and then the horizontal line is the damping value. And it's, as I scroll, it's just moving all over the place because each of those local fits is finding the frequency at a different position. Okay. Anything else?
Okay, we have a, yeah, I got a follow-on to that, to this. It says, what I meant by accuracy of the parameters is that sometimes when curve fitting, there are some extraneous modes with damping ratios are very far off, and I usually disregard them. What is the source of these modes? How can I rely on the estimated damping ratio? Should I use half power or some of the FRFs? Oh, excuse me. Should I use half power on some of the FRFs and compare with the emiscope values?
Okay. I think I
Let me
get the
read that
gist of
one.
that question. Well, no,
Okay.
he's
You
asking
might be, you
about,
could probably, yeah.
well, when the damping estimates are way out of, see here we've got different damping estimates between the local and the global. But they're not, they're in the ballpark. I mean, here's one, it's the local is 4.9, the global is still 5.57. So you might ask yourself, well, and that is the half power point or the 3 dB point or what we call the damping decay constant. I prefer to look at the damping in hertz because that is the width of the resonance peak, and it's also the decay in the time domain. That's the coefficient of the exponential decay. So when those numbers are relatively the same, that's saying, you know, the curve fitting, yeah, it's a little different between the local and global, but not orders of magnitude. So all of these fits are within the range of acceptable results. If we had a mode estimate with, or let's just say a damping estimate on a particular measurement of 100, or here's the mode is at 2,000 hertz. If the damping were 100 hertz and all the other estimates were 5 hertz, I'd say we call that a computational mode. So that we get a lot of computational modes when we use the stability diagram and some of these methods in here. These methods will throw out a lot of computational modes. Now I prefer to use the polynomial fitter in short bands like this because I can control where the curve fitting occurs. With the stability diagram, I need to use all of my data, and I can have all sorts of spurious noise in my data, 60 cycle noise from electrical noise and multiples of that. So I can steer around all those issues by using the polynomial fitter in small bands. And again, I can use scripting. If we have time, Mark, I can show another example where I use scripting to go through and curve fit a number of bands of data. And I've even got some bad data so that with the scripting I can tell it where to curve fit and come up with some usable mode shapes. Again, the statistics is a nice way to say whether you're doing a good job, but looking at damping, throwing away the spurious damping estimates and spurious frequency estimates, and then looking at your mode shapes and animation is really the best way to, as we were doing back here, you can see the difference between, let me put this down for a minute, go back, and there's a global fit. Let's see, we were on, well, we're not normalized, so you can see that mode shape is, because there's so much complexity in it, I don't expect to see that from a lightly damped structure, but that's what the global fitter gave me. Here's what the local fitter gave me, a much cleaner looking mode shape. So again, looking at the animated picture is a good way to judge whether your curve fitting results are acceptable or not. I hope that answered that question. Generally speaking, if you use the but we can go back and use the stability diagram and use one of those fitters and see what it comes up with. Let me go back and get that data. It's going to have the same problem because all of the turn this off. With the stability diagram, I want to make sure I use a large band of data because these curve fitters don't work well. So let me just go ahead. This is going to curve fit all this data using 1 modes, 2 modes, all the way up to a maximum model size of 50 modes. So let me go ahead and run that, and we'll see what it comes up with here. Okay, well, it did a pretty good job on this data, but out here where we found the local modes, again, you know, I could go ahead and just, now what this is showing me is if I have a stable estimate that's within this tolerance, the frequency is within 4 hertz, the damping is within 4 hertz, I've got at least 5 modes that meet those 2 requirements. But again, this is a global fitter. So if I go ahead and, well, let me save these estimates. I'm just going to blindly go ahead and say, gee, it all looks good to me. Let's just save those groups. I got 21 modes there. Let me go and just look at the fit function with this particular fitter. Okay, well, it did what appears to be a nice job. The frac value is at 8.7, not great, but we've fit over a very large band of data. You can see that the low frequencies are very good. The high frequencies, there we got a very poor match of that mode. Well, I may want to go in there and delete some of it. If you look at the damping estimates, they're all reasonable, except when I get to these higher frequencies, the damping is getting a little bit higher. So those could be curve fitting errors versus, now what I would do there is just compare some of these estimates with the local fitter, what we did earlier, where we just went in and picked a band of data and curve fit it. I mean, this, and the final solution would be to go ahead and, well, let's just add I'm going to add all of these modes to what we just did, and let's go back and that's not the one I want. Okay, so here is my shape table. Let me just arrange things a little bit here. Now there's our local fit. If we go down here, let's see, that was 2100. So here's the one that we got from the stability diagram, right there. Not bad. There's a little bit of there's certainly some phase in there. Now there's a poor estimate. I mean, I'm just looking at it and saying that doesn't look reasonable. That looks like a pretty good estimate there. Again, you know, as you get familiar with your data, you can see that what this global fitter is doing here when I've got mass loading, it's doing the best job it can to fit these high frequency modes, but they all have mass loading in them. And see, here's 2 of them right here at the same frequency, almost the same damping. So, you know, if I just blindly go through and fit my data, I may get some very strange looking mode shapes. Let's go down here and look at the, now there is a rigid body mode way down. We didn't fit anything down that low, or we didn't go down there and look, but there's our first flexible mode. Not bad from the stability curve fitter. So these are the same results that I would expect from using a local fitter, going through in smaller bands, and using scripting to automate, you know, setting up my bands, using the quick fit. Quick fit is really the easiest curve fitter to use to get familiar with your data, but you can see all these mode shapes are coming out very, very clean. There's not a lot of complexity. Here I get up to the one that we were fitting before, the 2000 hertz, and it's got 5.59. That's roughly what we got from the local fitter, but you can see there's a lot of complexity in there. Again, if I normalize it by taking that complexity out, the mode shape looks a little cleaner. All right, I think we spent almost an hour. Mark, do we have any other questions?
Not at this time. We do not have any. We have about 10 minutes left. If somebody has a quick question, you can go ahead and raise your hand, and I can unmute you. If you see the little hand over there in the go to webinar panel, you can click on that and raise your hand, and I'll go ahead and unmute you, and you can verbally ask your question. No questions at this time right now.
Well, you guys are all being too timid. You should ask the question, and even if it sounds to you like a dumb question, we will answer it, because there's really no dumb questions. We want to answer your questions. But you can see how when I switched over to normalizing, this is a very handy thing to do, even though your curve fitting results are kind of complex, and we've got mass loading on this in this data set of data. If I normalize those shapes, what that means is that I'm resolving all the phase angles to 0 and 180. And we won't go into the details of how that happens, but on this data, it's I can control it. I can go through each mode and kind of set up a boundary. If you look down here in the shape table, all the phases now are 0 and 180. So the software automatically did that. If I turn it off, you'll see that it goes back to, well, come on. It didn't update my display for me. Okay, there we go. So if I click now on these mode shapes, you can see the phases are not 0 and 180 anymore for these high frequency modes where the mass loading effects were the greatest. Let's go to there's a 2 kilohertz mode that we did the local fit on before. You can see phases are all over the place. If I go up here and look at, here's the local fit data right there versus the stability fit. You know, the phases are different, but when I animate them from the local fit, well, if you look at these phases, 359, that's almost 0. 360 would be 0. 175, 184, 330. You have to look at the magnitude along with the phase. So when we're down in the noise, the 954 here, the 330 is not going to show up as much in the animation. Now if I go here to the stability fit, you can see I've got phases that are 30, 205, 215. That's why this animation is showing a lot of complexity. Now if I go to normalize, it will replace the phase with 0 and 180. Now the shape is nice and smooth, nice and clean. Normal modes come out of an FEA model. So I started off talking about FEA models. We didn't look at those mode shapes, but we did look at some of them. And those all have phases of 0 and 180. Experimental data, and especially after I curve fit it, chances are none of the phases are going to come out 0 and 180. They're going to come out something different. However, when I animate good curve fit results, right there, it doesn't matter whether I'm normalizing or not. Okay, so there it is normalized. This is our local fit. But if I turn that normalization off, and then I have to update, now I'm animating the complex data, but it looks virtually the same. Okay, I guess that's it, Mark. We're burned our time. No more questions.
No more questions. If you do have some follow-up questions, please email us at webinar@vibetech.com. Again, that's webinar@vibetech.com, and we can go ahead and get those questions answered for you in an email. Next month, we'll be back again with another webinar. We don't have a title quite yet, but we'll get that out to you in the VibeTech newsletter, which will be out here probably the first, second week of August. So with that, we'll go ahead and wrap it up. We also, one last thing, we did record this session, so we will be posting this up to our YouTube page. If you go to YouTube and search on Vibrant Technology, you can get access to all of the webinars, not just this one, but an archive of all of our past webinars as well, and some additional tutorial videos.
Good. All right.
All right.
Well, I want to
go
say
ahead and end it with
bye,
that.
and thank you for coming.
Thanks. Bye-bye.
Bye.